that is a vector and he's rotating, okay, with respect to ej omega n. That's one way to understand ej omega n. Second way to understand ej omega n. I'll plot three things. Okay, I'm going to run it for you again. It's a bit fast. One is the real versus the imaginary. Sorry, this is the real part versus time. This is the imaginary part versus time. This is the polar plot. This is the 3D plot of the same thing. So you see three different views of the same guy. So how to explain that few figures that I have just shown you? The first one is, do you all know Euler's identity? Yes, Ej theta equals to cos theta plus J sin theta. Okay, why is plus minus? Then you see plus minus here. Why? Because if it's Ej plus, then we'll use cos theta plus. If it's E minus j theta, you will use cos theta minus j sin theta. That's it. Okay? Now, this is the real part. This is the imaginary part. So Ej theta gives you a complex number. Now, the equation that we are interested in a general form is Aej omega n plus phi, there's no n here. Okay, so I made a mistake. Later on, I'll put the n inside, a to the power of n, the n will go inside. A to the power of n, we'll leave it alone. This Ej, this expression, we'll use this Euler identity and we'll open it up and we get this. It is this that I was plotting. When a is 1, what will happen, guys? When a is 1, as n increases, what will happen to this side? 1 to the power of n is 1. So it will stay there. The only thing that is moving is this guy, and he's going to rotate. When a is less than 1, just now what I plot for you is 0.95. After a while, a 0.95 to the power of 1, 0.95 to the power of 2 will become smaller and smaller. That is why the phasor is rotating and becomes smaller and smaller. Okay? So you're going to figure it out. All right. So this was what I've just said. In this example, I plot a equals to 0.95 and omega equals to pi over 4. What does small omega means again, sir? What is its name? It has a name. Its name is digital frequency. And it has a unit. Its unit is radian per sample. I'm going to move along, and each time I move along, I'm moving by one sample, correct? And I've told you that you are going to move by pi over 4. So I ask you, in how many samples does it take to move one round? Quiz question again. 8, because 8 times pi is 8 pi, divided by 4 is 2 pi. So it's 8 samples. So how do I see that it's 8 samples again? You count, guys. 1, 2, 3, 4, 5, 6, 7, 8. This guy and this guy, if it was flat, it's the same point. Correct? Same. In the sign, 1, 2, 3, 4, 5, 6, 7, 8. This guy and this guy are the same point. Right? One cycle. What about this one? Same. He's here. He's going to rotate one round in 8 samples. First point, second point, third, fourth, fifth, sixth, seventh, 8. Well, if you shift it, you can see it. All right? And now, yeah. So why do we bother? Since I've already introduced the sinusoid, why do I bother with the complex exponential? It is because in secondary school, in high school, in A levels, in poly, you all think that sinusoid is the most important signal, but that's not true. Because sinusoids And cosine, sine and cosine, they are cousin. They are nothing but phase shift of each other. So why do you have two guys, right? They are only just phase shift, 90 degrees phase shift of each other. Therefore, there must be something simpler. The something simpler is our friend, okay, which has the cosine and the sine. So why? What's the interesting thing? You can represent the cosine with this equation. How? Cosine of this is nothing but cos omega n plus this plus j sine. This guy plus E minus. Do you know how to derive the cosine from the Euler? Let's try. Okay, E minus j theta equals to cos what? Cos theta minus. Then if I want to add these two guys up, what will happen? Cos and cos is 2 cos theta, right? The complex exponential becomes gone. Yes? So this is E plus j theta plus E minus j theta. I don't like the 2. What do? I have cos theta representing. Minus. What will happen, guys? What will happen? Cos will become 0, right? Sine? Sine becomes plus 2j sine theta, right? So this is minus, right? So I don't like the 2j. Finish. Yes? That's it. Now, so what I have just said, we have said that Fourier likes to decompose signal into small little parts. And in fact, we always use a complex exponential. Yeah? We'll use a Fourier analysis to break a signal into complex exponential, sum of complex exponential. All right? And then, because I already told you, the cosine and the sines are complex exponential. Therefore, our friend here, the sine and the cosine are eigenfunction. Therefore, our friend here must also be an eigenfunction. What does an eigenfunction mean? Let's try again. An eigenfunction, A, E, J, omega n, goes into a system LTI. Outcomes what? If A comes in, outcomes B, yeah? Some amplitude is changed, friend. Can? E, J, what? Same omega, same frequency that is rotating, omega n plus phase. He will change amplitude and he will change phase. But the frequency omega remains the same. Can? That is an eigenfunction. All right? And that's why we are very interested in this signal, because he's an eigenfunction. He can make up cosine and sine, and then he can be used to form any signal that you want. Now, I've already shown you that the phasor is rotating. One guy is rotating anti-clockwise. I haven't shown you rotating clockwise yet. Can? So you go and figure out. When omega is between 0 to pi, he will rotate this way. If he is from 0 to minus pi, he will rotate this way. One is rotating clockwise for omega. For another different omega, he's rotating anti-clockwise. Okay? I'll do this last slide very fast. And the slides just say that the omega that we are interested in is not unique. Every time omega plus 2 pi, the frequency you have observed is the same. What does it mean? Let's use my hand moving again. My hand is moving by pi over 4. Okay? Here is first sample, second sample, 45 degrees, right? Pi over 4. Yeah? Pi over 4. Okay? Okay. Let me move 2 pi plus pi over 4. My signal is here, right? 2 pi plus pi over 4, each omega. 2 pi is what, guys? And pi over 4. Where did I land? Exactly like pi over 4. So now, without even doing any maths, you already know why this is true. Okay? The even more interesting one is this. I'm not moving. My omega is 0. Every sample, am I moving? No, omega is 0. Okay? But now omega is 2 pi. To you, I have not moved. Because your eyes open, n equals to 0, n equals to 1, n equals to 2. If your eyes have been open like real time, right? You have seen me move. But your eyes were like discrete time. Open your eyes, close your eyes, open your eyes. Can you see now? So that's the magic of, then the difference between continuous time guys and discrete time guys. Discrete time guys sleeping all the time, huh? Right? sleeping until you open your eyes again. Okay? Whatever happened in between, you don't know. No idea whatsoever. All right. So you have done all this, then we have reached the end of signals, and then we are going to operations. Okay? Thank you.